Hello and welcome to part 2 of our Hillslopes and landslides lecture. In part 1, we covered weathering and diffusive hillslope processes, and I asked you to think about this question of, based on diffusion processes that we talked about, where do you expect to find these slow hillslope movements? And now we're going to turn and think about the advective hillslope motions or landslides. And we're going to think about how hazardous different types of hillslope movements are, and we'll think about why they occur. In doing so, our aim is going to be to look at the risk of landslides through looking at the hazards associated with each and thinking about the occurrence of each around the world. And for your homework in particular, you are thinking about one location in the world that is near and dear to you. All right, so we'll dive right into slides. We're going to talk about a range of slide types. Each of these has a different hazard and different occurrences that form the risk. We may not talk about the occurrences right away. However, we're going to get into the different factors that drive hill slopes. And so that's going to allow you to interpolate what you think the occurrence is for different locations around the world. These slides are going to be differentiated by the type of material that's involved. And so that's going to try and tie this back to the first part of the lecture when we talked about weathering. So I'm going to go through several slide types. We're going to start out with slides that mostly involved soil at the top of this diagram. Then we'll go into types that involve debris. So that's going to be the soil plus the deeper regolith. And then we'll end with slides that involve bedrock. Okay, so we'll start out with soil. And the first one of these I'd like to talk about are earth flows. Earth flows are these dumbbell-shaped landslides. So what I mean by that is they have a wide area that's called the source. And this is where it's eroding and taking material from. It has this skinny area where it flows. And then it has another large area where it deposits. This is also called the toe. This is the bottom of the landslide, and it's where it's going to bring all of that material from the source downslope into usually a valley. Earth flows are going to be driven usually by rainwater, and so they're more common during wet seasons and in areas that have a fair amount of soil water. But they are relatively slow movements. They can be long lasting. So there are earth flows that have been moving for much of our historic record and that we've continually monitored. However, despite the fact that they may last for decades or a century, they tend to be fairly slow. And so their hazard can be predicted. If we know where an earth flow is and we're constantly monitoring it, then there's not much that it'll suddenly do to us that we don't expect. On the left are two examples of what earth flows look like. The smaller one on the upper left has less of that characteristic dumbbell shape, but we still have an area where we see the soil being sourced from. We have a small transport zone, and then we have the toe where it's being deposited. On the lower left is a much larger earth flow, and we're only looking at the bottom, so you can just catch the top of the transport zone. And then most of this here is that depositional toe. One of the things that characterizes the earth flow is this really fluid-like form to it. Because it is moving fairly slowly, it doesn't get a chaotic rubble look to it. Instead, we can see kind of these ripple-like features that indicate the motion. Also characteristic of this in this lower case is you can see trees growing on this earth flow. So this is another indication that it has fairly slow movement that's not too chaotic. If trees are able to still grow there and still remain upright. In contrast to that relatively slower and steady movement of soil, we can have translational slides. These occur again in the soil layer, so they're very shallow, but they occur very rapidly. So unlike earth flows, they're going to present a bit more of a hazard because all of that material is going to come at once, and we don't really have any prior monitoring to show that it was moving already. These tend to occur through a failure of the soil on top of some weaker material. And so often this has to do with water. You have a large rain event, that water is going to penetrate into the soil and form a weak layer. So it kind of lubricates the soil, and it may cause some sliding of that topsoil layer in a translational slide. So these can be triggered by water. We also see them associated with earthquakes. So in areas that are prone to large earthquakes and have a lot of hill slopes, we worry about translational slides occurring after the earthquake. If you wanted to model a translational slide, it can be pretty easily done through Candy. This is a nice example where we have a hard biscuit layer. That would be the bedrock. We have this caramel layer, which you could think of as the water. So immediately after a rainstorm, that water is going to get into the ground and sort of pond on top of the bedrock. And then on top of that is the chocolate, which is the soil. And once you elevate that onto a small slope, it starts to move simply because that weaker material, the caramel or the water, allows it to slide along and slide off the bedrock. Okay, so we'll move a little bit deeper now. So now we're thinking about debris, the mixture of soil as well as other parts of the regolith and loose transportable pieces of bedrock. And the most common, or one of the common slides that we see with debris are debris flows. These are going to be triggered by rain. So this is again an area where we need precip. And they need to be in steep valleys that have loose sediments. There needs to have been some weathering to prime the landscape. These are very rapid and hazardous. So the debris flow is going to, through the water, it's going to transport soil and mobile bits of the regolith, which creates what's called a slurry. So rather than this being water mixed with soil, this actually becomes a new fluid that is a mixture of water and soil. This gives it new density properties, and it actually allows it to float large boulders. And so debris flows can have this extra element of hazard because the density of the fluid within them is different than normal density, and it's able to carry a lot larger debris, which can create another layer of hazard. It creates what's these characteristic levee walls. And so in this picture, we're looking down the middle of an old debris flow. So in the center here is where the debris flow flowed through, and it moved down slope. And on the sides of the debris flow, this is where the larger material that the debris flow is carrying is kind of pushed to the side. And so it forms what are called levees, which looks a lot like river levees. And these kind of just show where the debris flow track was. Okay, so another type of slide that uses debris is a rotational slide. And this can include the soil, it can include some regolith, usually doesn't include too much bedrock. However, these are deep slides, so they could potentially cut into that bedrock. They're characterized by a rotational movement of material. So in this diagram in the upper left, you can see that the failure plane is this bowl-shaped form, and the material within the slide is moving through rotation from its position in the upper part of the slide, or its original position, and it's rotating through that bowl and then coming up into the depositional toe of the landslide where it is deposited. Rotational slides tend to be rapid, and they can also be sort of reused or remobilized, be a good word for it. So because they rely on these failure planes at depth, these failure planes can persist over periods of time. And so you may get a rotational slide that occurs once, and then several years later, there's another slide that takes advantage of that same failure plane or of some smaller failure planes within the original slide. So this could be a recurring hazard. An example of this is the La Conchita series of slides. So in 1995, part of the hill slope failed above the town of La Conchita, which then was reactivated in 2005. And if we zoom back, we can see, here's outline of the 1995 slide and then the 2005 slide. And you can see just next to that is evidence of a larger rotational slide nearby. So this is an example of how these can be reactivated and can be a recurring hazard. Okay, and last but not least, we think about slides that occur just in bedrock. So now we're not really thinking about areas that have been weathered to have soil or any regolith. We get into rock falls. These rock falls are pretty much what they sound like. They are gravity-driven free fall of rock that relies on detachment of bedrock rather than mobilization of that loose regolith or soil. Since they're gravity-driven, they don't necessarily need to rely on water priming it. A lot of the previous slides that we talked about are really dependent on the presence of water or precipitation to drive them. However, rock falls, we are going to see these closer to cliff faces, where there is that potential for free fall. In both the examples in the upper right, we see this as kind of small discrete events that occur just along the edge. So we've just got a couple blocks falling off in D and just a little bit of the cliff falling off in E. However, these can also range to a much larger scale. So this example that's shown in the lower left, you've got a very large mass of the cliff that falls off and slides off. And because that is so large, as it falls, it remobilizes into what's called a rock avalanche. And so this is still involving mostly bedrock, but now it has somewhat fluidized its form. And instead of falling and leaving behind just chunks of rock at the base of the cliff, it actually is able to flow a lot further in a somewhat more coherent mass. So this is a good reminder that all of these slide types that we've talked about are on a spectrum and they can change type mid-movement. So you may start out with something that is an earth flow, and through maybe a rain event or a steepened slope, you may get a debris flow forming from that earth flow, right? So these are continuums, and we should think of the hazards associated with each as potentially transferring along. So now that we understand what main landslide types are, I want to now flip to thinking about what drives this landslide motion, because this is going to inform us what the occurrence of each landslide type is in a particular landscape. So we're going to try and distill all the drivers of landslide motion into two categories: the forces that are resisting motion versus forces that are driving motion. So what on the landscape makes this soil and the regolith stay where it is versus what is trying to make it fall? And there's going to be four main factors that I'd like to talk about. So the first of these, that is resisting the motion, is simply what is the rock made of or the hill slope made of? What size is the soil in the hill slope? And this is going to be important because it lends itself to the internal strength of that rock or that soil. A nice way to think of the internal strength of the rock or the soil is to think of the angle of repose. So if you were to stack that soil material by itself, completely dry with no vegetation, if you just stack it in a pile, what is the angle that that pile forms? So if you played with this at the beach, you know, as you're building a sandcastle, wet sand or dry sand doesn't really form a great sandcastle because it tends to fall apart, and it tends to fall apart into a pile that has a about 35-degree angle to it. And this is the angle of internal strength of sand. If you add water to it, you add a little bit more cohesion, and it can stand at steeper angles. That, however, is going to be an effect of the water. So that's not related to this internal strength. The internal strength is just the dry material. From this diagram, we can see how that angle of repose varies. So fine sand will tend to settle at an angle of repose of 35 degrees. Coarser sand has a slightly steeper angle of 40 degrees, and pebbles a bit steeper at 45 degrees. So how does this relate to hill slopes? Well, if you have a hill slope that's made of fine sand, it can really only stand up to slopes of 35 degrees. Above 35 degrees, the internal strength starts to fail, and so you're more likely to get hill slope failure in that fine sand. However, if you had that same hill slope made of angular pebbles, it could stand up to angles of 45 degrees before the internal strength fails. Okay, the other main force that's going to resist motion is vegetation. And this is really part of cohesion as a whole. So even though that soil particles, they may want to fail on a slope greater than a certain angle, if you have things like vegetation there, it can help anchor the material to the deeper parent material or to the deeper bedrock, right? So in this example, we have an area of soil, which I've outlined in red here. And then we have a tree with its roots penetrating through that soil and binding that soil into the deeper bedrock here through its roots. And this can add quite a significant amount of cohesion that allows that soil to stay on the hill slope, even if it is above the angle of internal strength. Okay, on the flip side though, we have things that can drive motion. So even though we talked about, your wet sand on the beach can actually strengthen material, it turns out water, more often than not, actually decreases the strength of the hill slope and drives hill slope failure and drives landsliding. And the reason for this is that water is going to create a buoyant force that decreases the effective weight of the hill slope. So just like your rubber ducky floats because of buoyant forces, so do all of your soil particles. They may not actually float, but they may be effectively lighter, right? So just to recap on the buoyant forces, if you have a grain or some material that is in water, you have the gravitational pull that's based on the mass and the density of that material, and that pulls it down. However, you also have the pressure of all of the water around that, and so the pressure is going to be lower on the top of that material because there's less water on the top. And it's going to be greater on the bottom because there's more water height on the bottom. And so this drives a buoyant force where overall the water is actually pushing up on that material. Depending on the weight of the material, that could cause it to float like the rubber ducky, or it could cause it to sink. However, in sinking, it still has a lower total gravitational pull than it did before it was in water. And this is going to be true for soil. The soil is still in a scenario where it sinks. However, its mass, its density is now being slightly offset by the buoyant force of water. And so there is less gravity holding it to the hill slope than there was previously. And so it's going to be more likely to fail. All right, and the last main driving force may be fairly intuitive, but it's going to be the slope. The steeper slope you're on, the more gravity is pulling down on that material, and the more the material is likely to fail. So if you have a steep slope here and you have some box of soil on top of it, right, we have gravity pulling directly down on that. And we could separate this gravity out into two components, right? Two vectors of gravity, one that is parallel to the slope of the hill slope and one that is perpendicular to it. And the steeper the hill slope is, the stronger this force parallel to the hill slope is going to be. And it's this force that is pulling the material down, right? And just in contrast to that, here's our shallower slope with the material, same weight, but now if we do that same force vectors, you can see that the size of that parallel vector is a lot smaller than it was in this first example on the steep slope. Okay, so as you're thinking about what the occurrence is of a landslide, you want to keep in mind these four forces or these four factors. What's the rock soil type? What's the vegetation? Is there vegetation? What's the water condition? Are you in an area that gets a lot of precipitation or not? And then what's the slope? However, there are a few other things that can prime a hill slope for sliding. So one thing that we already talked about with rotational slides are whether or not the slides are on a pre-existing hill slope failure. That could cause them to recur. So we showed this example earlier of La Conchita failing in 1995 and 2005 with a much older failure behind it. Another example of this is the Oso, Washington landslide in 2014, and that failed suddenly and unfortunately destroyed a community on Stillwater Drive. It was a very unfortunate accident, but when we look at it from a geologic perspective, and we look at the landscape around it, we can see evidence that there were pre-existing hill slope failures that could have been used to warn this community. And so as an aside, this is another call for action to sort of integrate more of our geologic knowledge with public communication and public access to that knowledge. I want to explain this image on the right a little bit because we haven't had a chance to look at this yet. This is a DEM or digital elevation model, and it shows what the landslide or the landscape looks like if you were to strip it of trees. And so this is just essentially a topographic map, but filled in and shaded like there's a sun. So in this case, the sun is coming from up here and shining onto the landscape. We can see these scalloped features here. This is the head of the Oso landslide, and right next to it are other scalloped features, which are evidence of other landslides that are much older and are signs that this is a very landslide-prone area. Something else to think about that can prime a hill slope for sliding is the subsurface layers of the geology. So far we've talked about everything like the soil is all one type of soil. However, that's often not the case, and we may see stacked layers of soil or material that are all slightly different. Seattle, Washington is an example of an area like this, where if we looked, kind of dug a pit into the ground, we would see something like this stack here, or if we first started digging, we would get into gravels, and then maybe some more sand and gravel, and then we get into sands, and right below that sand, we would find a layer of clay. Now, clay does not let water through. It is very non-porous. That's one reason it's probably pretty good to use in pottery, because you can hold water in a pot made of clay. This is unfortunate though when we think about landsliding, and especially in a place like Seattle where we do get a lot of rain, because this means any water that falls on the ground surface will trickle its way through the gravels and the sands, it'll meet the clay, and it'll be held up there. And so we get ponding of water on top of the clay. And that ponding is going to affect the buoyant forces, just like we talked about a few slides ago with the main factors of hillslope failure. And by decreasing the effective weight of those sands, it's going to increase the likelihood of failure of those sands and gravels that lay on top of the clay. So this is a problem in Seattle. It's an important consideration when you're thinking about the likelihood or the occurrence of landslide hazards. Don't just look at what's right on the surface, but think of the layering and how they're interacting in terms of trapping water. Another example with clays are quick clays. And so this is an instance where we actually have a very unique type of clay. These are clays that were deposited in salt water. So originally when this ground was laid down, the clays were forming in a marine environment. So they were depositing in salt water and they have a lot of salt ions in them. Over time, the oceans receded, the land rose, and so there's no longer an interaction of the clays with salt water. Over time, too, rainwater is flushing through these clays and it's taking out the salt ions, and that weakens these clays. And eventually they fail in a type of landslide that's a quick clay slide. It's more fluidized than some other slides, and it has some characteristics of a rotational slide, kind of combined with characteristics of a rapid earth flow. So these are very rapid slides that have flow-like characteristics to them and really occur just because of this quick clay subsurface. So they're less reliant on what the slope is or these other main factors of landsliding. However, this is something we really only see in certain areas because you need that condition of clays being deposited in salt water. We tend to see them in many locations in Canada, such as near Quebec, and we tend to see them in Norway quite frequently. Okay, so at this point, we have gone over the formation of material that forms the slides through weathering, which forms regolith and soil. We went over diffusive sliding process or diffusive hillslope processes. So processes by which we can bring material down without causing catastrophic failure, so perhaps less of a hazard. And then we've gone over slides, which present more of a hazard. We've gone through many different slide types, including earth flows, debris flows, rock falls, and rotational slides. We've talked about the relative hazard of each of these. We then talked about what drives slide types or drives slide failure, which gets into the occurrence of slides. So now for your homework, I would like you to synthesize this in a conceptual diagram by choosing a location. This can be any location in the world that is up to you. It can be your hometown, it can be somewhere you dream of going once the pandemic is over. For that location, I would like you to, for earth flows, debris flows, rock falls, and rotational slides, think about the hazard associated with each slide type and then the potential occurrence of each slide type. So this is going to combine to be the risk, and I want you to communicate this through a conceptual diagram. I'm also going to ask that you include a 2 to 3 sentence justification, mostly because I don't know where you have chosen as your location, and so this just helps fine-tune and relate that occurrence to the location. As an example of what this conceptual diagram could look like, this is a nice conceptual diagram for rivers, which is our topic for tomorrow. And what you have here is basically the X and the Y axis have the variables on them. So in this case, channel type and channel pattern. And then in the middle are the actual channels. So for example, if you wanted to apply this to the hill slopes you'll be thinking about, you could have hazard an occurrence from low to high, and then at the kind of intersection of the correct hazard and occurrences, you would have the different slide types. And so their space within this diagram would tell you what the relative risk of each of these slide types are. So this is just one example of the conceptual diagram you could do, but you're free to use any design that you want to do.